be here, so I really appreciate the invitation. And I'm going to try to describe some things we know and don't know about complex systems. So I work with a number of complex systems, meaning they're physical, biological, or social systems that have a lot of pieces that strongly interact with each other. Physical systems such as motions of stars and gas and galaxies and motions in proteins, biological systems such as gene regulatory networks and the timing of heart attacks, and social systems such as models of sustainable peace and how therapists and clients interact in psychotherapy. And I teach a number of different kinds of courses, and we put some of the lectures of some of those courses online on YouTube. AC Forrest helped put the statistics course on methods in complex systems. And one of the courses I currently teach, Physics for Computer Science, is on a YouTube channel with the somewhat understated name of Smart Physics for Brilliant Computer Engineers, Season 2. And some of the books I've done involve nonlinear dynamics applied to life sciences and social sciences. And with Peter and his collaborators, I contributed to the book on destructive social relationships. And with Ula Stravinska-Zanka in Nova, Southeastern University in Fort Lauderdale, we did an edited book on mathematical modeling of social relationships that came out over the summer. So what I'm going to do is talk about the general properties of different types of complexity and illustrate that with some specific examples to see what we can learn by looking at some of those specific examples. So there are lots of different mathematical formulations that you can use to analyze complex systems. And sometimes I think any one person that works using one type of system thinks that one type of system applies to everything. And it doesn't really. So there can be ordinary differential equations that have few variables or many variables. There can be partial differential equations, which mean things spread in space as well as time. I'll describe self-organizing critical systems soon. Boolean networks, which means truths and falses are connected by elements like ors and ands. Other kinds of networks. Multiplex networks or systems where maybe we have a whole bunch of social interactions at one level and a whole bunch of economic interactions at another level, and those different networks interact with each other. Complex adaptive systems, artificial neural networks, which are now called deep learning, and agent-based models. So there's a lot of different things. Many of these systems have attractors, which means it's a steady state that the system returns to. Even if you push it off, it sort of comes back to where it was. And some of these systems may have none or a few or many attractors, and there may be different dynamics in approaching the steady state or cycles around it or much more complicated behavior. Now, some of these systems have many variables, and for each variable creates a different dimension. So I want to describe a little bit how important these high-dimensional systems, how important high dimensionality is in these systems. So to give you a sense of dimensionality, you could fit, how many people are in the world right now? This is an old slide. 8 billion. So when I did this slide, there were only 7.5 billion people in the world. But you could fit all those people in a one-dimensional line, as if they're waiting for the M4 bus on Broadway, and that line would be about 1 million miles long. But if you put them standing on the squares of a checkerboard in a two-dimensional area, you could basically fit everyone in the space the size of New York City. And I had seen a cartoon once, which I couldn't find for this talk, where they had everyone from Asia in Brooklyn and Queens, and everyone from Europe in the Bronx, and so on. And if you had people standing on each other's shoulders, you could fit everyone in the whole world in a cube that was about a mile on each side. So as you go to higher dimensions, there's more and more space in things, and that qualitatively changes things. I can say it in a different way as well. In a one-dimensional or two-dimensional space, if you have a random walk, you're guaranteed to return where you started from. But in three and higher dimensions, you never get back to where you started from. And what that means is that if we're going over a hyperdimensional landscape, it means we're never likely to get back to where we started from. And this raises very important issues about sustainability and what sustainability means if we really have this high dimensional system with many variables. Another aspect, we're used to seeing so-called rough landscapes that look like this, with mountains and valleys. But this isn't really very rough. This is a two-dimensional surface that we're looking at bent and twisted into a three-dimensional area. As we get up, and even on this surface, there are things called saddle points. So it's like this pass between the two mountains. You would fall down into the saddle, but then in the saddle, you'd fall off of it. And in a higher dimensional space, we're going to have hyperdimensional saddles. And what that means is this system is going to slip from one of these unstable points to another, and it's going to wander around in this very high dimensional space. And again, this raises this issue of, can we ever have sustainability here? And what does sustainability mean? Does that mean we have to put constraints on the system? And is that what we want to do? Do we want to prevent the system from doing what it's naturally doing? Another odd thing about these high-dimensional systems is when they go through a really dramatic change called a bifurcation, it turns out you can represent that by a change in only one variable, even though there's a large number of variables in the system. This is called the center manifold theorem. So there are a lot of interesting properties of systems that have a large number of dimensions. Another interesting thing is the role that negative things play in systems like this. So in pattern formation proposed very brilliantly by Alan Turing, where there is a short-range stimulation and long-range inhibition, it means that local areas self-reinforce but then inhibit the areas next to them, but that allows areas further away to self-reinforce. And so you can get patterns like stripes or spots on tigers and a lot of other interesting things, or on seashells. So the negativity plays a role in creating a much more complex pattern. And we see these in neural circuits, which are both excitatory and inhibitory. We see these in genes and even in the processing of messenger RNA, where things are enhanced or turned off. We see this in social networks with the interaction between cooperation and competition. We see this is a very technical aside, so if this makes no sense to you, this is okay. But in the wave function in quantum mechanics, as Scott Aronson has pointed out, that those coefficients are either negative sometimes or complex numbers. And that's what leads to quantum mechanics being different from classical physics. So negativity is not necessarily bad. It can lead to finer and faster control in a system. We'll see that it can lead to networks that are more tightly functioning together, and it can lead to pattern formation.
So the negativity, you're just talking about blocking, inhibition, that kind of force?
Yeah. Something you could think of it as a negative feedback loop, but it can also be thought of as something bad happening, that having a little bit of conflict is useful, maybe not too much. So we want to see that that's an important element to play in systems. Another interesting thing that at least living complex systems do is they have an odd mixture of digital and analog. So when we build systems, maybe we have a digital to analog converter at the beginning or an analog to digital converter at the end, but they're not constantly mixed. In living systems, they have nerve cells which have a digital signal of spike trains, which then ends in a synapse that squirts out analog neurotransmitters, maybe so they can add up together at the synapse, and then that goes to the next neuron, which is digital again. So we have this interesting alternation. And the same thing with us. So we have DNA, which is a 4-letter digital code, but then the organism makes proteins which are analog things and structural things, and it's the shapes of the proteins that do their biochemical reactions. We don't understand at all what advantage is gained by switching between digital and analog like this, that biology is using like this, and we never seem to do that. There are networks of things that are very important in a lot of different complex systems, and there are a lot of different kinds of networks. So typically, everything is not connected to everything else because this is actually the same reason why they have multiple elevator chains in large buildings. Because if every elevator went to every floor, you'd fill up the whole volume of the building with elevators. So you can't have everything connected with everything else. Sometimes there are random connections. More typically, they have small world connections. So things are connected to their neighbors, but every once in a while there's a longer range connection. So there's only a few degrees of separation between one node and the other node in the network. Very often there are hubs. This is an airline map. So some of these cities like Chicago and this city in Texas, which I can't read, and somewhere in the Northeast are forming hubs. So not everything is connected, but there are some nodes that have much larger connections. There can also be hierarchical connections that maybe things sit within each other, and then the whole group is connected. These are those multiplex networks that I described before, where we may have a layer of environment and climate and a layer of social, economics, or culture, which are then connected. Many of these networks have this peculiar characteristic of having long or fat-tailed distributions. And shown over here on a log-log plot, this line is actually what a normal or Gaussian distribution would look like. Every time I mention Gaussian distributions in my class, I actually have a picture of Gauss from an old Deutsche Mark bill in my wallet, and I usually don't take it out because they're sick of me taking it. But I have it, but I won't take it out again. But I do have a picture of Gauss in my wallet. And so on this log-log plot, this is what a Gaussian distribution looks like, but this is what a power law distribution looks like. So for many of these situations, you have a much higher than expected probability of having a node that has a large number of connections or an unusual event happening. And people underestimate how often they should see a black swan. Going from global to the micro level in gene regulatory networks and neural networks and in ecological networks, if you have 3 nodes, each representing different things in each of these networks, there are 13 ways they could be connected to each other. But in all 3 of these networks, actually, they're predominantly connected only by this these types of connections shown here at number 5. And this is called a feed-forward loop. So this node affects that node, this node affects that node, and one of them is a controlling node to do that. So the microstructure of many networks has some interesting features that are units that then cascade up to lead to more global structures. So most of the models that we've built are structural models. You think you understand how something works. So you write down equations that represent it. You solve those equations using an appropriate mathematical method. Increasingly in science, we're building what I call process models, which is you say how the pieces interact, what the process is going to be, and then you just run the computer and you see what happens. And these models include the self-organizing critical systems, which I promised I would talk about but haven't done yet, but will. Iterative functions, cellular automata, complex adaptive systems, agent-based models, machine learning, artificial intelligence. Increasingly, this bothers people because you know the rules and you see the result, but you can't understand how those rules led to that result. And people seem increasingly disturbed by this. So the only thing I can say to that is recall Larry Ellison's comment about the lack of privacy in the computer world, which is get used to it. That's the direction we seem to be going in. What we'd like to know about a system. We would like to know if it's sustainable. Is it robust to challenges that are internal or external? Is it really about to do something different that we're not expecting? Has it few or many important variables? Does it have independent subsystems? Does it have these sort of architectures I've been describing that we can detect? And does it have identifiable types of dynamical properties we should expect from it? So those are sort of general properties of systems. I want to talk about 3 specific systems to give you a sense of what those systems do, so you not only understand what they do, but how they're different from each other. And let me make sure I actually turn this on, which I did. This is a system, a model originally going back to Lord Rayleigh 100 years ago, further developed by Salzman here at Columbia, and explored further by Lorentz at MIT. And it's a model for the atmosphere. So you say the atmosphere is heated from below at the Earth's surface, and it's cooled from the top. And we all know that hot air rises. So the air from the bottom here will rise to the top. When it's cold at the top, it's going to fall back down. So we have these convective rolls. But look what these convective rolls do. They're mixing the hot air from the bottom with the cold air from the top. So as they turn over, they actually reduce the force that's driving the convection. So eventually, they slow down, and then maybe they start to turn again in the same direction they were turning in, or maybe they start to turn in the opposite direction. So Lorentz represented this system by 3 equations and 3 variables, one of which x is the amount of angular rotation, which is plotted here. So here it was negative, the system was going counterclockwise. Eventually it slowed down, but it went counterclockwise again, but then it slowed down and went clockwise, and it's the number of things. We can represent the x, y, z values as a point in x, y, z space, and we can let that point evolve in time, and if we do that, it doesn't fill up the entire x, y, z space. This system only wants to have certain combinations of these 3 variables, and that set of combinations is called an attractor. And the attractor has certain properties, so if we start the system away from the attractor, it doesn't want to be there. And so it relaxes back onto the attractor exponentially fast. On the other hand, if we start 2 points on the attractor, they also separate from each other exponentially fast. So even though we set up the system very close to each other, this one is turning clockwise and this red one is turning the opposite direction, counterclockwise. So this means the system has what's called sensitivity to initial conditions. So here I've done a numerical integration starting at 1, and here starting ever so close, 1.00001. Couldn't get much closer than that. And they both do the same thing for a while, but look, after a while, This one is turning clockwise, and this one is turning clockwise. And this is what's called the butterfly effect, that if the butterfly beats its wings in one of these places, then it will change the weather a week later and cause a thunderstorm in one of those places. And I still lament that when I got all of these from different articles, I didn't keep the references from where they came from to be able to put here, but I'm not doing this again. So what this means is that each time we run the system, we'll get a different time series. Somewhere maybe in middle school, they told you if you set up a system in science, you should be able to run it and get the same result. Here, every time we run the system, we get a different result. But if we make a plot of that x value a little bit later from where it was before, we can actually reconstruct the attractor. So each of those time series just is moving along different parts of the same attractor. What's real in this system is not the time series. What's real is a transformation of the time series to show this attractor, which is the same every time. Or to say it mathematically, this is the true invariant of the system. The time series are not invariants of the system. Now you would think this sort of chaos and sensitivity is bad, but it can actually be very good. In a linear system, if we want to change the output of the system, we have to change a control parameter an awful lot because it's linear. But in a chaotic system, if it's very sensitive to a control parameter, we may need to change the control parameter only a little bit in order to make the system do what we want it to do. And this is an example. This is actually data from Roy at the University of Maryland. So this is the fluctuations in intensity of a laser as a function of time. And by understanding how to control the parameters of the laser with these very small pulses, he can actually make the laser much more regular. And he can actually do some other fancier tricks with the laser that I'm not showing here. Another aspect of these sort of systems is that if the system has a very deep energy minimum that it can fall into, then it's going to be pretty stuck here and it may bounce around a little bit. So there's not a lot of noise that it produces. But if it's a very shallow minimum, especially one near only a shallow hill, it can roll quite a lot. And sometimes it might roll over the edge to a different attractor. So if it can roll around a lot, there'll be a lot of noise. So sometimes noise is a signature that we may wind up someplace else rather soon. So some things are chaotic. The properties they have are sensitivity to initial conditions. They have this phase space, which is where the invariant is, and maybe we can control them. But many things are not low dimensional. And we see there both words, many and not, are in caps here. They do not have the properties of low-dimensional systems. And I think weather and climate are examples of things that are not low-dimensional. So here's an example of a not low-dimensional system. This is the self-organized critical system. You drop one grain of sand at a time and it forms a sand pile. And the edge of the sand pile will reach a point where if there's too much sand, there'll be an avalanche and the sand will come off. So what's interesting about this system, you probably think systems like to live at equilibrium. This system lives poised just at the maximally unstable point because the avalanche will carry things just so it's stable again. So this is called a critical system because it's poised between stable and unstable, like water evaporating into steam. And it's called a self-organizing system because it automatically organizes itself to be at that point. These systems produce interesting behavior. So this is a log-log plot of the number of avalanches against the avalanche size. And this is basically a 1 over size or 1 over f type of plot. So these systems make fractals in a number of different ways. They make power law distributions. Mathematically, any system where we keep adding to it and where the amount added exceeds a threshold, and that threshold is then relieved by being sent to its neighbors, will have these properties. So this has been used as a model of earthquakes because we have stress building up. The earthquake relieves the stress, but it sends it to its neighbors. And also forest fires and epidemics and a number of social and economic systems as well. So let's look at the difference between chaos and self-organizing criticality. The chaos is ordinary differential equations. SOC are partial equations, meaning they spread in space and time. The chaos is low dimensional. It only has a few variables. The SOC is high dimensional. Each grain of sand is really its own actor. Chaos has clearly defined attractors. SOC doesn't. Chaos one.
Do you want to be interrupted in the middle of your talk?
Sure.
Why are you saying there's no attractors in a high-dimensional system? Isn't it just a high-dimensional attractor?
Yes and no. So the attractors in the chaotic systems are really pushing the system toward an energy minimum. And in one sense, we're not doing that in the SOC. In a more technical sense, the approach to the attractors in chaotic systems is exponentially fast. And actually, in high-dimensional systems, very often it's algebraic. So there are different properties. They're not the same kind of, you could say the sand pile is always going to be a certain shape, but it's not the same thing. It's qualitatively different than the way we would think of an attractor in a chaotic system.
I'll talk to you.
Okay, we can talk, fine. The difference here is that the chaotic system wants to live in a stable equilibrium, and the self-organizing critical system is living between equilibrium. And the chaotic system may shed some noise before a change, and we don't have that in the SOC. So the point I'm trying to make with this is not all complex systems are the same or have the same properties. So this is another example. This, yeah.
So I'm very curious about this, whether the world is actually relapsing to some stable state, and whether there's some healthy mean reversion and the chaos going back to some. So on this slide, though, self-organized sounds pretty good, right? But at the same time, you're saying it's actually the most chaotic that's possible.
No, it's pretty good, but the good here means you're poised at a phase transition. So the system is self-organized to be at a phase transition, which means the slope or the sand pile, as opposed to being in an energy minimum. So in that sense, these two types of processes are maximizing something different. So if you look at a system, I mean, one of the questions, what should the general rule be? So we have some rules. We think entropy is increasing all the time. We sort of think things should be going toward equilibrium. This is an example of a system that's not always going to equilibrium. So all I'm saying is that there's no single few general properties that we can say any complex system has. And here I'm trying to differentiate between low-dimensional systems and high-dimensional systems. So the point I'm trying to make here is there are many different kinds of systems. To get back to that energy surface I showed before, if there are, we don't know when we have a high-dimensional, we don't know if all high-dimensional systems behave the same way. We don't know if some high-dimensional systems have a much larger number of saddles than other high-dimensional systems. And if that's true, some systems may wander a lot more in their space that they can do and never get back to where they start from. And others sort of, what you're saying, may be more sustainable and may hang around in the same places more. And we don't know how to look at a system with a lot of variables to be able to tell, which of those two cases it's more likely to be. So that's why this talk is entitled What We Know and What We Don't Know. So this is another specific example. This was done with Lev at the end of the table and his students and collaborators. So this was a model of 512 people that are living connected in a small world. And even though everyone is not connected to all the others, there's a short path to go from one person to another. And each person is, so each node, each person has a value. And each person is trying to duplicate the value the other person has or does the opposite of that. So we have a mixture of how many people are doing the same and how many are doing the opposite, and what is the shortest distance that they are effectively connected to. So this is the result of that calculation. So the way to read this picture, a horizontal line is the value of each person at a given time. And as that evolves downward, that's how the values change in time. So if most people do the opposite of each other, you get very small regions where they're doing the same thing because everyone is trying to do the opposite. And since we start the calculation with a little randomness in the initial values, we get regions which are very small and different from each other. On the other hand, if people are trying mostly to do the same as their neighbors, we get much larger regions because they're all trying to do the same thing. We still get regions that are different because, again, we've seeded them at the beginning with some random values. And so we're going to get different regions. What's interesting about this, both people doing the opposite and people doing the same both freeze relatively early. The situation remains constant from that point on. And we don't think that's very good. If there's a mixture of people doing the same and the opposite, it sort of bubbles along a little bit. There's a little more variation in what's happening. And we think in general it's good not to be too fixed and not to be too random because this gives you the ability to respond to changes in the environment. So we think this is probably a better place to be. We can look at that another way. Here, the red and blue dots represent two runs of the system. And if most people are doing the opposite, they sort of build on each other to be further separated, or the same thing happens if they're the same. Here on the two runs, the mixtures of the red and blue are overlapping because we have a lot of those very different regions. Here, everyone wound up doing not so well, and here in red, everyone wound up doing much better. But if there's a mixture of people, you can see that the total variation in the system is less. They're closer together on multiple runs here. So we think that, doing the opposite is not necessarily bad, that somehow it's tying the system together in a way that's interesting.
It shows blue and red as default colors.
I have a different slide where there's a more complex interpretation of red, and I always do a warning label before that. I didn't do that here.
Is 60-40 crystallized into the stripes?
Do you want to say anything on that? Is there a turnover point?
When you have like a half, so that the final state is, so that is like a skeleton of the final state, right?
And in terms of like 60%, would that be closer to the 50-50 or closer to the 90%? Okay. So here, the global properties depend both on how people are connected and what their behaviors are. And it's interesting that doing the same and doing the opposite in a certain way has some similarities. But having an equal mix actually, we think, makes the system function better. So this is also a very strong argument for diversity, and that having diverse elements in the system makes the system overall better.
Sir, can you just elaborate what better means?
Okay, here better means, so one way of thinking of better is that you shouldn't be too frozen and you shouldn't be too random.
Or flexible or adaptive.
Right, so because we think that if you're bubbling a little bit, then if something changes, you're poised to respond to it. But if you're doing too many weird stuff, you won't have a coherent response. So this is sort of an old edge of chaos argument that you should have some flexibility, but not too much. Some variation, but not too much. So the conclusions here, the global properties depend how people are connected and on their behaviors. This, I think, I already said. The other questions this raises are also interesting. That is, so really start with number 2. In a lot of these models, including models we've been making, we're basically looking at pairwise interactions. And this is true in the causal loop diagrams also. We always have things pairwise, as opposed to having things 3 at a time connected. And maybe the question comes up, can we build all pairwise interactions, all n-order interactions from just pairwise interactions? So the example I give in my class of the difference between this is the interaction with Bob and his wife, and when Bob's wife is not present, Bob's girlfriend, he has an interaction with her. But when both Bob's wife and girlfriend are present, those pairwise interactions are very different. So the deeper sense, of this also is we have some understanding, but not the best understanding, of how the topology of the network determines the dynamics of the system. We know more about the structure of networks, of how things are connected, than an understanding, if we build a certain network, what's going to happen on it. So the lessons from here are the importance of topology, of how things are connected, are there leverage points, is it hierarchical, and the role of these negative interactions. And negative isn't always bad. So this is a third example of this. This is from the Sustainable Peace Project, that most previous research studies have analyzed peace only in a negative way, as the absence of conflict, violence, or war. And there's a growing effort to understand positive peace, the political, economic, and social systems that generate and sustain peaceful societies. So this project, Peter Coleman and Josh Fisher and Beth Fisher Yoshida and Doug Fry in Alabama and Philip Vanderbroek in Brussels and Danny Burns in the UK and a large number of other people began initially with a review of the literature and then a survey with responses from many different people from many different disciplines, a small and a large workshop, input from a number of other organizations. And my role or small role in this is to turn their qualitative models into mathematical models and to try to use data science methods to measure those peace factors. And what they had been doing is creating these causal loop diagrams, which force you to identify what you think are the individual elements in the system, the positive and negative feedback loops. And as Danny Burns would say, probably the most important aspect of this is the process. That if you have a whole bunch of people around the table which really means a whiteboard with Post-its, that you have people from different backgrounds and different expertise and different experiences, that allows you to interact, and it's that interaction that helps pull out more of the individual elements and how they interact with each other to create an integrative complexity. But this also has limitations. If one element changes and the next element changes, it's very hard to chase through this very complex mesh of interactions as to what's going to happen. And these elements themselves have no quantitative value, even though intuitively we think some things should influence others more strongly. So this is the core engine of this causal loop diagram. And the two most important central elements are positive and negative intergroup reciprocity. That is, that if you do something good to someone, do they do something good in return, or do they spit in your face? And this is essential. This is all based at the intergroup level. But these two central factors are also influenced by people's view of the past, by the expectation of their future, by social norms and other things. And the group has been expanding this into a larger and larger number of areas of all the things that influence the core engine, which is in this central blue here. So this just illustrates the fact, first of all, that I can do PowerPoint with no hands. But if we have social norms that in this case are interacting with, I said no hands, sustainability, in this case interacting with negative social process, the red are negative interactions, the light blue are positive interactions, then sustainable processes will interact with influences from the government in a positive way, and the government will interact in a positive way with information flow throughout the system, and in a negative way trying to reduce negative intergroup reciprocity. And negative intergroup reciprocity has all these other negative effects in the system.
Something you have a chaotic effect.
Right. Okay. So what we've been doing to try to understand how all these things interact. Yeah.
Just to watch the time a little bit. It's in 5-10 minutes, then I'll start trying to close out.
Okay. So.
We'll have some time for questions.
Okay. So all right. So all I want to say about this is that we developed a mathematical form of this model and a graphic user interface and a program, so you can run this from initial conditions. It solves the ordinary differential equations numerically. You can change the input, initial conditions. You can change the connections by pointing and clicking and changing things. And so we've made this available as open source on GitHub. And what we've been doing is using databases and looking at social media to try to measure some of these things. So to measure intergroup reciprocity, we've identified fans of different football teams in London and Northern Ireland, and then see whether those same people use pro or anti-immigrant hashtags. And at least for these football teams, there's a nice mixture of people, which is actually a good sign. And we've done things like look at tweets from those same areas and identify words that refer to the past or the future, and then do a sentiment analysis of those tweets to see that at least around before New Year's, people had a much higher positive sense of the future than the past, and that was positive than random tweets. So let me sort of get to what this whole project raises is real questions about how this network of interactions works for sustainable peace. Is it flat the way I've pictured it so far? Are there hierarchies within the network? What are the real roles of negative factors? So the system always goes negative because people's negative reactions hurt deeper and longer, but we can overcome them by having either many positive or more strongly positive or leverage points. This also means that it's situationally dependent. Different things can fix a bad situation, and different things may be needed in a different situation. Overall, what we don't know about complex systems, we're not really sure in general how many variables we need to measure. We don't know what the most important structural properties or types of connections we should look for, and we're not sure what dynamical features we should expect or what we should be looking for that are the most significant. And in the deepest sense, we don't have a clear sense of what all the possibilities are. So the take-home lesson for this, so I'm just struggling to get some, so we can get questions which are more important than listening to me talk, are there are lots of different kinds of complexities. And we know some kinds of complexities and their properties, but we're not sure how to identify types of complexities in given systems. And we can in some systems, but not in many. And it's likely we don't know all the different kinds of complexities that there are. So let me end there and let me save this, and then we can ask questions. So let me, before